present the work that I did as a part of my master thesis work at the Institute of Neuroinformatics under the supervision of Dr. Malika Paivan. Yeah, so before I go into the presentation, I wanted to already give the take-home messages, sort of to guide the entire presentation. So we demonstrated online few-shot learning on a novel energy-efficient hardware architecture. I mentioned hardware architecture because the chip is not taped out yet, and everything that I show today is based on simulations. However, we used hardware calibrated learning. So the models are actually informed by the statistics of the devices. So we expect it to be closely matched to what we see here today, the results that we see here today with the software simulations. We show that constraining the network architecture to a specific layout does not terminally determine the performance of a model. And we show the importance of inner loop dynamics in a meta-learning algorithm known as MAML, and we highlight why we need hardware and software co-design. So sort of a high-level view of the project is we take a novel energy-efficient architecture, we combine it with the versatility of a meta-learning algorithm, and on top of that, we had some hardware-aware training to emulate the physics of the substrate. First, let's look at the background and introduction about the novel energy efficient architecture. So in the current von Neumann architectures, we have something known as the memory wall problem. So we have the memory, we have the compute, and the energy it takes to shuttle the data between the memory and compute is much larger than the operation itself. In order to mitigate this, we moved into non-von Neumann architectures, such as near memory compute, where we make it as close as possible. We get the memory as close as possible to the CPU to reduce the power consumption, or even better, in-memory compute, where the memory and compute are co-located. William Chapman yesterday gave a really good introduction to such systems. So I'm just going to build on top of that. Basically, these are arranged as a crossbar architecture, and in-memory compute can be in many different forms. And here I specifically talk about analog in-memory compute using resistive random access memory, that is RRAMs, also known as the memristors. So as the name suggests, they are resistors with some sort of memory, so they are non-volatile. We program the resistance and we give an input along the row of the crossbar, and we can collect the outputs on the columns of the crossbar by the virtue of Ohm's law. So this emulates a matrix vector multiplication, which is the prominent operation in neural networks. But the problem comes when we try to scale this in-memory compute crossbar. So when we try to scale the system, the physics kicks in, and we have parasitic resistance or capacitance of the metal wire and large read current, etc. So one possible solution will be to distribute these crossbars into a multi-core architecture. However, if there is too much communication between these cores, the memory wall problem sort of resurfaces. This is most probably the case for fully connected neural networks, where each neuron is connected to every other neuron in the next layer. So to mitigate this, our lab came up with a new hardware architecture inspired by the brain. So we looked into the brain, and one of the most prominent network architectures in the brain is known as a small world network. A small world network is characterized by two features. So the first one is that they have a very high clustering coefficient. So every neuron is connected to every other neuron. However, the total number of connections is comparatively low compared to a fully connected network. So we can imagine it as clusters of neurons that are highly interconnected, and these clusters are sparsely connected to each other. So the hardware architecture that we proposed recently is known as the neuromorphic mosaic. The neuromorphic mosaic is a spiking neural network accelerator based on non-von Neumann style systolic architecture. It's systolic architecture in the sense it basically has green tiles, which are the neuron cores, and the blue tiles, which are the routing cores. And we sort of arrange them in a pattern, in a repeating pattern. And these basically use distributed Memristor-based crossbars for in-memory computing and routing. And we demonstrated magnitudes efficiency in routing compared to other neuromorphic solutions such as TrueNorth or Dynapse. I recommend you to check out the paper for the exact figures. And what this does is basically it efficiently implements a small world graph. So if I zoom in a little bit, we see that there is a neuron tile, which is highlighted in green. So we have neuron circuits, which are recurrently connected neurons. So we have the recurrent weights and the external weights. External weights are the weights that are the synaptic connections in other neuron cores. And we have the routing tile, which is basically a Memristor crossbar with some amplifiers, which sparsely connects these neuron tiles together. While this mitigates the problem that I just mentioned, edge computing comes with its own challenges. So we have sensory environmental noise, we have domain data shifts, or the need to learn new tasks that the model was not trained for. And the RRAM devices themselves comes with a lot of non-idealities. Recently, Stewart et al. Suggested that we can leverage meta-learning in order to do online learning in neuromorphic edge devices. And Demirag et al. Showed that meta-learning can also be used to overcome the non-idealities associated with RRAM. So that sets the stage for the next section that I want to talk about. That's the meta-learning algorithm. I'm going to quickly skip through this as soon as possible. Because this is not the major contribution of my work, I'm just using a most prominent meta-learning algorithm. So model agnostic meta-learning, or MAML for short, is a meta-learning algorithm that's basically taking a learning to learn approach. So the goal of the algorithm is to learn a very good initialization so that when we provide it with few short data, it can rapidly fine-tune for the new set of tasks. It is gradient-based, so it's efficient and easier to train comparatively. So before I explain a bit more about MAML, I need to quickly talk about the task that we are using. So for few-shot learning, a task is characterized by n-way k-shot. So n-way meaning the number of different classes that you're trying to classify. And the k-shot is the number of samples per class that I give you. So this is an example of a three-way two-shot task. And the data loader for meta-learning algorithms are a little bit different from traditional machine learning. So as in traditional machine learning, we have the training set and the testing set. But in turn, we split them into two other sets, so a support set and a query set. The support set can be imagined as the training set within the training set. So basically, we use the support set to fine-tune the model, and we use the query set to evaluate how the model performs based on the fine-tuning that we just did. This will be the life cycle of MAML. We just talked about the data sample right now. And here comes the bi-level optimization. So we have an inner loop and an outer loop. In the inner loop, we try to get task-specific weights. Okay, task-specific weights that are phi of I. So we use the support set, we calculate the loss with respect to theta, and we change theta or update theta to get phi of I. And we do this for several inner loop updates. And later, we use these task-specific weights and estimate the loss on the query set. And based on this loss, we calculate gradients on initial theta. So we don't use phi now. We double differentiate into theta and change the initial parameters. So this can be imagined as pulling the theta towards your local minima, but not actually keeping it at the local minima, because we are pulling it closer to a distribution from where we can rapidly fine-tune to learn the new task. This is the testing phase of MAML, where the outer loop is out of the equation, because after training, we fix theta, and every time we receive a new task, we're going to fine-tune to that particular task and calculate only the task-specific weights. We use the spiking Heidelberg digits dataset, which is a keyword spotting task that is audio-based classification dataset with the corresponding spike trains and the output labels are given. So it has 20 classes, spoken digits from 0 to 9 in both English and German. So yeah, we are trying to do few shot learning, but in order to learn a new nice initialization, we need a lot of data. And for that, we augmented the data as spatial sampling along the frequency channels. So from the 700 initial channels, we are trying to reduce the dimensionality to 256. So we sample along the frequency channel at regular intervals and concatenate the respective channels together. So if I try to reduce the dimensionality to 256, I can get 3 spike trains from a single spike train. So this makes my data 3 times larger, but also reduces the parameters from 700 input parameters from 700 to 256, and also helps with overcoming overfitting of the model. One interesting aspect is that here we are preserving the time order of the spikes. So this does not affect the input data in any way. SHT is not inherently a few-shot learning data set. So we basically converted it into a few-shot learning data loader by arranging the SHT into n-way k-shot data. So the model architecture that we use a single recurrent spiking neural network with 256 leak integrated fire neurons with 20 output neurons, one for each class in the SHT. So we use layer sequential unit variance initialization. The interesting thing is that in the inner loop that I just mentioned, we use stochastic gradient descent. And for the outer loop, we use the Adam optimizer. So as introduced before, during the testing phase or after deployment over the edge, the outer loop is out of the picture. So we only have the inner loop, which has to be efficient because Adam is more sophisticated. However, it needs to store all the momentum estimates for all the parameters during training. So we used SGD for edge deployment, and we used Adam optimizer in the outer loop in order to converge to a nice minimum. We use softmax cross entropy loss on the VMAN to train the network and BPTT using surrogate gradients. One important thing to note is that this surrogate gradient, for surrogate gradient, we used a fast sigmoid function, which is double differentiable. So it's compatible with MAML. All right. Now comes the hardware-aware training part. So since we wanted to emulate the behavior of the hardware, we have several constraints that needs to be taken into account during training. The first one is that we update only the output layer weights in the inner loop. So in order to update all the weights, we need to calculate gradients and store them on chip, which is highly inefficient with energy and area. The meta-learning, the paper which leveraged meta-learning for neuromorphic devices basically mentions that for MAML, it's enough to train only the output layer weights because MAML inherently learns the data distribution as the fundamental data as in the penultimate layers and only uses the readout layers to adapt for learning new data representation. We use one inner loop gradient step. So as I mentioned before, traditional MAML goes on for several inner loops in order to settle for a nice local minima. But owing to hardware constraints, we stop with one inner loop gradient step. One-shot learning is ideal, but with SHT, one-shot data was not enough for learning. So we used 5-shot data, which translates to a memory buffer, which holds 5 samples. We used a very high inner loop learning rate because if we use a small learning rate, we are going to get small gradients, which translate to very small delta W, which is highly precise. But the RAM devices that the Mosaic is made of is of low precision. So we used a very large learning rate, which in turn gives rise to bigger gradients, which in turn has less precise DWs. And this goes well with mammal because mammal needs a very large learning rate for the inner loop in order to learn new data distributions. Now, for RM-aware training, so for a regular neural network, this will be the forward and backward pass. So we have the input, we multiply it with the weights, and we pass it through a nonlinearity, and we get our prediction during the forward pass. And for backpropagating the errors, we calculate the difference between your target and your output, and we backpropagate the errors in the backward pass. So on hardware, this is like this, and the weight will be the conductance of your memristor. But here's the dirty part. The memristor is noisy, so you can't specifically program a weight. So what I mean is that we program some conductance, but with time, this is going to deviate and drift apart. So to account for this, we use something known as memristor-aware training, or where we use straight-through estimators to decouple the weights. So in the forward pass to the weight, we add 5% Gaussian noise of the largest weight in the layer. And during the backward pass, we use the actual weight and update the actual weight, which corresponds to, which basically learns to stay within the region that does, even during the drift, accounts for the conductance. So one specific thing is that not any neural network can be programmed on the mosaic. It should be a small world network in order to be efficient. So this will be the connectivity matrix of a random fully connected network. However, we need something like that, where the diagonal is strong, meaning that neurons that are closer to each other are highly connected, and the off diagonals are sparsely connected. So before I go into how we achieve that, we need to look into a hop matrix. So basically, let me take a toy example from the mosaic. So let's say we have 4 neuron tiles and 5 routing tiles. A hop matrix is nothing but how many routing tiles or how many hops you need to reach the other neuron tiles. So we can see that within a neuron tile, we have 0 hops. So all the neurons are connected to each other. So it's basically free. But when we need to go to other neuron tiles, we can see that for going to one or the first neuron tile or the second, we just need 1 routing tile, which translates to 1 hop. But for going from neuron tile 0 to 3, we need 3 routing tiles, which is highly costly. With that introduced, what we did is that we created a layout constraint mask, which basically calculates exponential penalty depending on the number of hops. So S is the layout constraint mask, which is exponential of beta, a regularization term, which basically adjusts how many hops are allowed. And H is the hop matrix that we just saw. So based on this, we create a loss term, the layout loss, which basically corresponds to each layer, each element-wise weights with the corresponding penalty. And we add this to the total loss of the system. So now the total loss consists of 2 terms. The first term is the cross entropy loss, which reduces the test error on the model performance. And we have the layout loss, which takes care of generating a small world network. So time to discuss the results. But before I go into that, I just want to quickly recap the experimental setup. So we have a single layer spiking neural network with 256 leaky integrated fire neurons. However, we also trained a fully connected baseline, which we restricted to 64 neurons in order to keep the total number of parameters equal. So we trained on 15 classes during the training phase. We excluded 5 classes. So while testing, we test on all the 20 classes and demonstrate the performance on seen and unseen classes. We used 5-way 5-shot task and 1 inner loop update. And first, we looked into the architecture of the network and the bit precision of the parameters. So this is the baseline that we created with fully connected network. We can see that on the trained classes, it achieves 70% accuracy, which is the standard benchmark for a single layer SRNN on SHD. And for the unseen classes, it exhibits around 45% accuracy. I have to mention that we always read out of 20 neurons, which basically translates to 5%. The chance accuracy is 5%. And now I show the results of a small world network, which is of high precision parameters. So we can see that on the trained classes, the accuracy takes a slight dip, but on the unseen classes, we see a very good increase in performance. And this can be attributed to the sparsity between the hidden layer and the output layer, because the same number of parameters are connected to 256 neurons as opposed to 64 neurons in the fully connected network. Finally, the small world network with the RAM-aware training, we see the highest accuracy on the trained classes, and we attribute this to the addition of noise during the training, which basically makes a network robust towards the samples. But we also see that the performance on unseen classes takes a slight hit. And this is basically because we only give 5-shot data and one inner loop update, which doesn't account for the noise as well as good as with the seen classes. So these are good results, but this can be made better. So we were thinking about the possible constraints that led to these results. And one possibility is that the number of inner loop updates is limiting the performance of the model. So to verify that, we increase the number of inner loop updates to 5 and 10. And this graph is self-explanatory. We can see that the model's performance is increasing with the number of inner loop updates. And with 10 inner loop updates, we get very good accuracy. Even on the unseen class, we get around 70% accuracy with just 5-shot data. I will quickly discuss 2 findings. So we found an interesting relationship between the inner loop and the outer loop learning rates with respect to the number of inner loop updates. This has never been reported before in any literature, which is also because no one uses a single inner loop update with MAML. So we did a Bayesian hyperparameter search. And for one inner loop gradient step, we can see that the outer loop learning rate is much more important than an inner loop learning rate. However, if we use 10 inner loop gradient steps, then this kind of reverses, and the inner loop learning rate is much more important than the outer loop learning rate. A frequent question that I get asked whenever I present this work is that, okay, can we use single inner loop update, but retrain the model with the same task for like 10 times? Would this compensate for multiple gradient steps? So it's better if we visualize what happens during the inner loop updates. So we have the meta-trained parameters, which are fixed. And from that, we do 3 inner loop updates here in this example. So the model kind of fine-tunes to a local minima. However, if we retrain, we are again starting from the same set of parameters, and we will reach an area in the loss landscape, which is similar to all the previously trained fine-tuned weights. So again, I would like to restate the take-home messages. We demonstrated online few-shot learning on the Mosaic architecture. We showed that constraining the network during training does not affect the performance. And we show the importance of inner loop dynamics in MAML. And we also highlight that. So I would like to elaborate a little bit on this point. Basically, the Mosaic as such, if we tape out now, it doesn't have any mechanism to support multiple inner loop updates. In order to do that, now we know that the performance of the model is much more when we use 10 inner loop updates. So it will be an addition in the hardware design where we can have high precision memory only for the readout weights, which can accumulate gradients and can help with multiple inner loop steps. With this, I would like to thank Dr. Melika Pewan and E. Demirag, who supervised this project. Also, Professor Herbert Hager from University of Groningen, who was my internal supervisor. Emre Nefci, with whom I had lots of intellectual discussions regarding this project. And finally, the Emerging Intelligence Subspace Lab of Melika Pewan, and the grant that supported this project, Metaspend of Horizon Europe. Thank you.